And welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. Today, we're going to be looking again at the fractional factorial design and its aliasing problems. In this case, we're going to do some de-aliasing to fix the aliasing issues that we saw in the last lecture. So as we saw, when running a fractional factorial design, we have a problem with effects being aliased with other effects. The way we're going to fix that is through follow-up experiments. We're going to run a second experiment with the goal of de-aliasing our first experiment and hopefully being able to determine where the significance is coming from. I think there's a squirrel over there. Never mind. And welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. Today, we're going to go further into fractional factorial designs. What we're going to do is expand on what we did last time, because last time we discovered that when we try to reduce the sample size for a full factorial design, creating a fractional design, what we get is this problem with aliasing. And then if we find significance in one or more rows of our ANOVA table, we don't know exactly which effect that significance is coming from. It'll be coming from one or possibly more than one of a set of factors or effects, set of effects, interactions or main effects. So what we're going to be doing in this lecture is looking at follow-up designs, because when you run an experimental design, that's usually not the end of the story. You can always go back and you can collect more data. You can run a second experiment to collect more data, to study, to pinpoint and study some of the interesting things that you found in the first design. So what we're going to be discussing are different ways to do follow-up experiments for a fractional factorial design, specifically with the idea of de-aliasing, that is, removing this aliasing problem that we discovered in the last lecture. So how do we do that? Well, we're going to talk about that now. All right, so what we'll be doing today is expanding on what we did last time with the idea of a fractional factorial design. So why don't we start with, we'll just say de-aliasing a fractional factorial design. All right. So what we need to do is start off with an example of a fractional factorial design. I'm kind of hiding the design that I'm using down here in these boxes that I already copied into OneNote. But the design example that we will consider is a 2 to the 5 minus 2 design. Now, if you recall from last time, what that means is we have k equals 5 factors and q equals 2 defining relations. And what we're going to choose to coincide with the one from my notes is that we're going to consider I equal to 1, 2, 3, and also I equal to 3, 4, 5. Now again, these are two defining relations. The idea is that we took this triple three-way three-way interaction term, and we aliased it with the identity. Now we can no longer estimate anything to do with these two three-way interaction terms. There's no contrast, right? They're always taking the same value in the ANOVA table, and thus there's nothing to look for a difference in, because every time we estimate one of these main or interaction effects, we're just taking the difference of our data set cut in half. In this case, there's no other half to look at because we just threw it out. And as we talked about last time, when you have two defining relations, there's going to be a third defining relation, which is going to be 1, 2, 3 times 3, 4, 5. And as we noted, all of the elements 1 through 5 are idempotent in this case. When we square them, we get the identity. That is, they are their own inverse. So when 3 gets multiplied by 3 here, it vanishes. It becomes the identity. And what we're left with is 1, 2, 4, 5. So those are going to be the elements in our defining contrast subgroup, including, of course, the identity, which is always there because group theory. I think there are groups actually that group theory without the identity, but in this case, all our groups will have the identity element in them, the column of all ones, you could say. Okay, so we have this, and then if we go a little bit further, what we learned last time, let me move all these things down, because we don't need them yet. So what we learned last time, going back to some of the definitions that we discussed, this design has a resolution of what? It has a resolution of 3 because 1, 2, 3 has, and 3, 4, 5 have length 3, and 1, 2, 4, 5 has length 4. And remember, the resolution of a design is going to be the minimum length of any, I guess, across all of the elements of the defining contrast subgroup. So here we have 2 elements of length 3, 1 element of length 4. The resolution is 3 in this case. Now, oftentimes when you're trying to pick a design, you want to try to maximize the resolution. The bigger the resolution is, typically the better you're going to be doing with respect to troublesome aliasing relations. By the time you get to resolution 5, typically people are happy with that. And you'll see, if you read the literature out there, very often you see people discussing resolution 3, resolution 4, resolution 5. I haven't seen as much going beyond to resolution 6 and above, but perhaps there's also interest in that. Again, typically you'd want it as high as possible, but by the time you get to 5, things are looking nice. So one of the things we didn't discuss, last time, we did discuss the idea of clear and strongly clear. So let's bring that in and then look at how that plays with resolution. So last time we said that a design is called clear if all of the main effects and the two-way interactions are not aliased with other main or two-way interactions. So in this design, we can actually look at it down here. Actually, why don't I bring this back up? We'll bring the first guy up here. So this is what our design looks like. Make that bigger, and we can get this one away because we're not discussing it yet. Okay, so this is what our design looks like here. Again, the data size is only 8 observations compared to the 32 that we would have for a 2 to the 5 full factorial design. So again, that's another maybe noteworthy thing to put in here, is that n is equal to 8 is equal to 2 to the 3. So that's quite nice. It means that we have a much smaller sample size that we need to collect. Now what we see here is that, well, we have main effect 1 is aliased with 2, 3, and main effect 2 is aliased with 1, 3, and 3 with 1, 2, and 4 with 1, 5, and 5 with 1, 4. So what that means is that none of the main effects, and I believe also none of the two-way interactions are clear either. There should be 2 more that are missing here, right? Because again, if we have 8 observations, that's 7 degrees of freedom. That means we can have 7 columns of things to estimate. Now, here I have 1, 2, 3, 4, 5 corresponding to the main effects and their aliased interaction effects. There would be, I guess, 2 more columns corresponding to 2 more rows in our ANOVA table, which through a quick scan is probably going to be, well, I think 2, 5 doesn't seem to be. Maybe I'll throw that in here. Also, we would have that 2, 5 is aliased with 1, 3, 5. I'm doing this to check for clear and strongly clear factors. So that's why I'm actually writing this out again. But okay, we have 2, 5 is aliased. Multiplying 2, 5 by this gets 1, 3, 5. Multiplying it by that gets 2, 3, 4. And multiplying it by this last one gets me a 1, 4, which I don't think is, oh no, 1, 4 is already here. Of course it is. Hold on. As I did last time, these things can always be a little bit confusing. Did I pick the right design here for my example? That's the problem. I'm doing 2 different, I see. I'm using 2 different designs. This was the design we looked at in the last class, but what I actually wanted to do to reconstruct this table was not have 3, 4, 5, but have 1, 4, 5. Sorry about that. And then the interaction term would be 1, 2, 3 times 1, 4, 5, which would get me a 2, 3, 4, 5, because that's what I get for changing my example between lectures. A 2, 3, 4, 5. And everything that we talked about still follows. It's still going to be a resolution 3 design. 2, 3, 4, 5. Okay. So we still have a resolution 3 design. And now if I try to redo this aliasing that I was doing down in the bottom here, so I still maintain that, yeah, 2, 5 does not appear anywhere in the columns of this table. So if we take 2, 5 and we multiply it by everything here, what we end up with is a 2, 5 becomes, is aliased with 1, 3, 5 as before. It's also aliased with 1, 2, 4. And it's aliased with 3, 4. So 2, 5 is aliased with 3, 4. That means that effect is also not clear. It's not strongly clear, certainly, but it's not clear because it's not, it is aliased with another 2-way interaction. And there should be one more thing that we're missing here, which I'm going to guess is 2, 4, just based on the way the design looks. Yeah, I see a 2, 3, but I don't see a 2, 4. Good. So if we take our 2, 4, what we find is that that one is also aliased with 1, 3, 4. It's aliased with 1, 2, 5. Basically, we are swapping the 4 and the 5 basically everywhere. So we have a 1, 2, 5 here, and in the last case, we're going to have a 3, 5. And that looks good. Okay, so these would be the 7 things that we can estimate. And the point that I was trying to get to is that none of the main or two-way effects are clear or strongly clear, just to write it out. But of course, if they're not clear, they're not going to be strongly clear. Recall that a factor is clear, an effect, I should say, a main or a two-way interaction is clear if it's not aliased with any other main or two-way effect. And an effect is strongly clear if a one or two-way effect is strongly clear if it's not aliased with a 1, 2, or 3-way effect. So that is not the case here. And what I wanted to point out, which I didn't point out at the end of the last lecture, can continue to move this guy down. So in general, for a resolution, if we have a resolution 4 design then all main effects are clear. They could even be strongly clear, but at very least they are, in fact, they have to be clear. That's, I guess, the first fact. And this will put a little dot there. That's true. And the other thing is that for a resolution 5 design, all two-way, we'll say two-ways are clear, at least clear. Again, they could be strongly clear, but they have to at least be clear. And all mains are strongly clear. So this is why, again, people like resolution 4 or 5 designs. If you have a resolution 4 design, it is necessarily the case that your main effects can at worst be aliased with a third order interaction. And there we have some separation. And if we get significance there, we typically would say, okay, we're going to side with the main effect over a three-way interaction because that's probably where the significance is coming from. And even a better case would be a resolution 5 design, because that means all of your main effects are now aliased with effects that are either 4-way or higher. So then you really have strong evidence that if you get significance in one of those rows of your ANOVA table, that is the main effect is where the significance is coming from and not a 4 or higher way interaction. So those are good things to be aware of. Now you can kind of get this pretty quickly. Let me continue to move down this table, which I copied over preemptively so that I don't mess up my recording when I switch out of OneNote to go get it. But I'll say, well, another in general, well, maybe we'll just say here, for a resolution R design, any I way interactions can at worst be aliased with an R minus I way interaction. And this really just comes down to, well, in some sense, staring at it in an example. So example, if I have something like I is equal to 1, 2, 3, 4, that's not a 4, 1, 2, 3, 4, 5, then what we would find is that, let's say 3 is aliased with 1, 2, 4, 5. So it's aliased with a 4-way interaction. If I take 1, 2, that's going to be aliased with 3, 4, 5. So it's aliased with a 3-way interaction and so on. So that kind of gives an example of what I mean by if I have an I-way interaction and I have a resolution R design, then at worst, we're going to have an R minus I-way interaction being aliased with our I-way interaction, which is kind of a strange sentence, but that's roughly the idea that I wanted to point out. So in summary, the point is that, yeah, we ideally, we would have a high resolution design, like a resolution 5 design, and not a resolution 3 design, like I started with up here, because in a resolution 3 design, some, if not all, of the main effects and interaction effects will be, well, not clear. There is a chance that you could have a resolution 3 design where some main effects are clear and some are not. It depends on the setting. But yeah, and also just to point out, you never want a resolution 2 design. Just as a, maybe I should write that in here. Based on what I said here with this R and I, basically never use res 2 because then two main effects will be aliased together. And that's just kind of dumb. Maybe there are some like really fringe cases where that's useful. To the best of my knowledge, that isn't the case, but you never know. Will be aliased together. And if you're going to have two main effects aliased together, it's like, why even bother testing them in the first place? Just pick one and test it rather than trying to test both, but not knowing which one is going to be significant. Like I said, maybe there are some really strange cases where you'd want to do that. But if you're doing that, there's probably a better design out there, like what we'll talk about at the end of the course, like the Plackett-Bergman designs, where you're testing lots and lots and lots of main effects, and you're going to get some crazy correlations in your design that we avoid in a nice factorial design. But that's a discussion for another lecture. So let's get rid of this guy once again, because he's even further down in what I want to discuss. The next thing I want to discuss is the idea of follow-up designs and de-aliasing. So the point, or the problem is what to do if we find a significant group of aliased effects. Well, what we could do is we could run a follow-up design. So one answer might just be report what you found and move on or whatever. But another answer, should you have the ability to replicate the study a second time, would be to, replicate the study, let's just say the design, with slight modifications to de-alias. Okay, so how do we do that? Well, what I want to do is go back up to the top and copy this guy for a second time so that we can hide him in here with there it is. We need that. We need to get rid of this guy because he is the next section of the notes. And we're going to do this. Okay. Almost. So the idea here is the example that we're doing is returning to the design, the 2 to the 5 minus 2 design with I equal to 1, 2, 3 equal to 1, 4, 5 equal to 2, 3, 4, 5. What we would find is that, let's say we found some significance in the first column here corresponding to main effect 1, two-way interaction 2, 3, and two-way interaction 4, 5. Now, again, we could just say, well, that significance is probably coming from the main effect factor 1, but we have two-way interactions which could somehow be like bleeding into the significance here, and we need to figure out what's going on. So what we could do is we could design a what they call fold over study to de-alias 1 from 2, 3 and 4, 5. So then the question is, well, how do we do that? Well, we do that by negating 1. Okay, what's that mean? That means we create another table where we flip the value of the first column, basically. So notice that here we have, well, my rows now seem to be slightly askew because of the way LaTeX decides to organize things. But the point is that these are the same. These are the same. These are the same. And these are the same. But these two columns are different. And they're different by flipping the signs, right? If we go back and replace the dot with a minus sign, then all I'm doing is saying, find another 8 participants for your study and do the exact same thing. But now for that first factor, factor 1, we're going to flip the value. And everything else is going to remain the same. So what does that actually do? Well, from a mathematical perspective, let me once again move this guy down further. So maybe we can get this all on the screen. Right, so from a math perspective, we have a new defining relation for table number 2, which is going to be -1 is equal to 2, 3 is equal to 4, 5. Or not a defining relation, sorry, an aliased group. And compared to what we had originally, which is 1 is equal to 2, 3 is equal to 4, 5. So what's going to happen is, as a result, we are going to now de-alias these, the column 1 from the interaction. So what we're basically going to do is, by combining these two relations together, we're going to destroy this equality. But we are still going to maintain this equality here. We're still going to have that 2, 3 is aliased with 4, 5, but it is no longer going to be aliased with 1. And what we can, how we can see that another way, besides me just sort of writing that, is to go up to here. Now, if I also flip the value of 1, then let me write this down here. So if I have my defining contrast subgroup, 1, 2, 3, 1, 4, 5, 2, 3, 4, 5, then by flipping the value of 1, what I'm effectively doing is deleting this, and I'm deleting this guy because they both have a 1 in them. And by flipping the 1, I have now kind of destroyed that aliasing relationship with the identity, because in the first set of the design, they would take the value of 1. They'd correspond to the identity. In the second design, they'd be negated and they'd be -1. So now they no longer coincide with the identity, whereas 2, 3, 4, 5 still does coincide with the identity in our follow-up design. So basically, what we're doing is we're taking the first table and we're taking the second table and we're cramming it together, and now we actually have 16 observations, and that is going to change the design that we're looking at. So by running a follow-up design here, or using this fold-over technique, what we've done is we've de-aliased 1 from its two-way interactions. And in fact, what we've just done is we have now turned, we've changed, let's say, maybe I'll write it on the side here. So we now have, well, we now have changed our 2 to the 5 minus 2 resolution 3 design into a 2 to the 5 minus 1 resolution 4 design, with the defining contrast subgroup just being the single element 2, 3, 4, 5. So what that means is that now elements 2, 3, 4, and 5 are all clear. They are aliased with three-way interactions, but they are no longer aliased with two-way interactions. And the element number 1, factor 1, I should say, is now strongly clear because it is aliased, I guess, with the five-way interaction 1, 2, 3, 4, 5. So in that case, we now have a much nicer setting for our design. And in fact, some of the two-way interactions, I think, should be strongly, though any two-way interaction involving 1 would also be strongly clear, because it would be aliased with a factor of or an effect of order 4. So yeah, this makes the design much nicer. Again, this is assuming that we can replicate the entire design. Now, there's one other thing that's worth noting, and that's that we have replicated our design. Presumably, this second table has occurred at a later date after we've already looked at the first table, and we said, okay, we want to run this design again to de-alias factor 1. Well, things can always change, and what that means is that we can include another column here. We can include a run column, or that takes on two values, basically run 1 and run 2. And we can use that column, that new column, to determine if there is some we can use that new column to determine if there's some significant change between the first time we ran the experiment and the second time we ran the experiment. So that is another good thing to be aware of. Again, in this case, I'll say with a run column included, we changed our 2 to the 5 minus 2 into a 2 to the 6 minus 2 design, because the run column can be treated as another factor in our design. And I guess we could go through and try to figure out what it's doing with respect to aliasing, though at this point, I think it would actually not be aliased with any of those other ones. So I think we should be okay. It'll be like a factor 6, which does not come into play with the defining contrast subgroup. So in some sense, it's not going to be that obstructive in this case. And so we would have a 2 to the 6 minus 2 design, which is still resolution 4 in this case. But again, it is important to look at that, because when you run the experiment again, whatever experiment you're running, there's a good chance that some things will change, and we can try to detect that change in the run column, or this new green column that we've included here. All right, so that's the idea of a fold over design. It's a way to run a second 2 to the k minus q design in order to de-alias some of the alias terms. So again, you can think of this as an iterative way of testing something. It's not so much that we just go out, design our experiment, collect our data, and we're done, but we go in with the mindset that we're going to run a small experiment, maybe 2 to the k minus q, where q is big, right? We have lots of aliasing relations. And then when we find out what's interesting, or what may be interesting in that first design, we go back and say, let's run the design again, but using this fold over technique to do de-aliasing. The point is that it can be more efficient to run a design this way, rather than collect, let's say, 16 data points at once. You collect 8. You look in your 8 and you say, okay, which one of these looks significant? And then based on that significance, you do a follow-up or a fold-over design that will target that specific term, like I did here with factor 1. I could have done the same thing with factor 2 or 3 or 4 or 5, for example. Though I guess in this case, if we target factor 1, we've already changed everything to a resolution 4, so it's probably good enough to just do it that way. If we targeted factor 2, we would or 3 or 4 or 5, we would still have a resolution 3 design, I think. Yeah, because we would lose the last term and one of the three-way terms, and we'd still have a three-way term, which means some of the effects would still not even be clear because it would be resolution 3. But if, for example, 2 was really interesting and we wanted to test that one, it's still worthwhile to have, I guess, a resolution 3 design and targeting factor 2 by de-aliasing it with as much as possible. All right, so that's something to keep in mind when you're designing your own experiments, that it's sometimes better to start small and then plan to replicate rather than just do everything, kind of like spend all your money at once designing one big experiment. So good rule to keep in mind going forward. But sometimes you don't have the funds to do an entire follow-up experiment. So then what do we do in that case? So let's move this guy. That's what this box is that I keep sliding further and further down the page. So the new thought is, well, what if we can't run another 2 to the k? That looks like a z. Let's try that again. 2 to the k minus q design, but can only collect another, let's see, what was the notation I was using for this case? Was it, did I choose a letter? I don't think I chose them. Oh, maybe I didn't. Oh, T. I was using T, I think, somewhere in here. Okay. We'll use T to try and coincide with my written lecture notes. Another T observations. Double question mark. So the idea, right, is that, again, start small, 2 to the k minus q, where q is big. Now we might want to do some type of follow-up experiment, but the problem is we can't replicate an entire 2 to the k minus q. It's too many data points. So what do we do if our funding body says you can only collect t more, or you can only include, say, t more people in your study? Now, if we can only include t more people in our study, what treatments do we give them, right? Because the idea here, and I've kind of given away an answer, but the idea of this table is, says, let's say we had the design from before, we had this 2 to the 5 minus 3 design, and we're told that we can go collect 2 more data points. So here we have a 2 to the 5 minus, 2 to the 5 minus 2 design with, let's say, t is equal to 2. So the question is how to choose rows 9 and 10. Now I have 2 rows filled in here, but the question is, how in the world do we choose what to test for 9 and 10? Because remember, every row is a treatment here. The treatment is a set of factor combinations. So again, if 1 through 5 is a cocktail of drugs that we're handing to some participant, I need to know which drugs to hand to the participant. So in this case, we've already tested, let's say, minus minus plus minus plus, and we've tested minus minus plus plus minus all the way down to the row 8, which is just plus 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 plus. So then the question is, well, what else can we do? There are, in this example, there are 2 to the 5, I guess, minus 8 choices. I can spell that right. Choices, right? Which is what, 32 minus 8 is 24, I guess, if I did that right. I think I did that right. Because for every input here, right, every setting, I can choose a plus or a minus. So it's 2 times 2 times 2 times 2 times 2. And I'm working under the assumption that I'm not going to replicate one of these rows above, but we might want to replicate one of the rows above. So I could even say, we'll say, or just 32, because maybe we want to replicate the rows above. I don't actually know. That's not going to be the answer, but how do we choose those rows? And we choose them now with respect to some type of a design criterion. So, oh yeah, I actually pointed out somewhere in here that and because we get to pick 2 new rows, there are 24 choices, choose 2, which is, I think, 276. I already calculated that beforehand. Options. Which means there are 276 different possible ways to choose rows 9 and 10. So that's a lot. And it makes you wonder, well, how are we going to pick them? So what we do is we try to pick them with respect to some type of optimality criterion. And this gets into the idea of an optimal design. So we pick them with respect to some optimality criterion, typically based on the design matrix X, or more specifically, based on X transpose X. When you multiply the design matrix by its transpose. Now we'll talk about different criterion. There are a lot of criterion out there. If you go to the Wikipedia page on optimal design, you're going to see like a dozen of them. And if you look in the literature, you'll find even more, because everybody has their own favorites. And this happens a lot in statistics, right? You have some notion and it's like, okay, well, we can have 20 different criterion to look at. Great. That doesn't really help me pick one. But there are some standard ones that are kind of the default option. So it is good to know that there are lots of design criteria out there. We'll just talk about a few of the most popular ones. Now, this table here was filled in with something called de-optimality. And de-optimality is, I think, the default in R, but I honestly would have to double check the package that I use to generate this. Now, there are R packages that will choose rows. So if you give it a design matrix and you say, I want to add in 2 or 10 or whatever more rows, it will then, with respect to a certain criteria, optimality criteria, it will find them for you, which is nice. Also, the choice of the rows is not necessarily unique. So just because we have an optimality criterion doesn't mean that there's one best choice. There could be a collection of best choices, right? Just because it's an optimal choice doesn't mean there's not another equivalently optimal choice. So these are all things to take into account when you're trying to run an experiment and using optimality criterion like this. Right, so then what are some optimality criterion? Well, the first one, and one of the most standard ones, is called de-optimality. And the idea here is we want to take the maximum of, or we want to maximize the determinant, which is a interesting minor typo I found in my notes. One more thing to change going forward. So the idea is that we want to, yes, and I was also using the notation X sub D, just to say that this is our design matrix, where X sub D is a matrix and it has 2 to the K minus Q plus T columns, and it has, I guess, rows and K columns. Yeah, because we have 2 to the k minus q treatments plus the extra t treatments that we're adding on. Oh, that's why I chose t, because it's an extra t treatments. Okay, so I did have a reason for doing that. Anyway, the idea of de-optimality is max the determinant of x transpose x with little sub d floating around here. Okay, why? Why would we want to maximize that determinant of x transpose x? Well, if you recall from, so then the question is why? Well, if you recall from linear regression, the least squares estimator is beta hat x transpose x inverse x transpose y, and the variance of the least squares estimator is going to look like sigma squared x transpose x inverse. So that's quite interesting, because that means if we maximizing this is the same, if we max the determinant of x transpose x, we are in fact minimizing the determinant of x transpose x inverse. And the determinant has a really interesting geometric interpretation. It's the volume of an ellipsoid. So if we wanted to create a confidence ellipsoid for beta, so beta hat is a vector in whatever dimensions we're in. We'll just say p, though I think it's, well, whatever, it doesn't really matter. Yeah, beta is a high dimensional vector. If we wanted to create a confidence set, sort of the multi-dimensional analog of a confidence interval for that beta, it's not going to look like an interval. It's not going to look like a square. It's going to look like an ellipsoid. And if we want to shrink that ellipsoid as much as possible, we want to maximize the determinant of x transpose x. So what I'll say is maxing the determinant will minimize the volume of the confidence two L's, one L, yeah, two L's, ellipsoid for beta hat. So in a sense, you're minimizing like the variance in a way. Again, it is a covariance matrix here, so you have to say, what does minimizing mean? But in a sense, you're kind of minimizing the variance of your estimate, and that's a reasonable thing to do. So if you say, okay, well, I can have an extra 2 observations, what observations will make sure that the variance is minimized as much as possible? That's a reasonable thing to try, and that's called de-optimality. Now, we have one that kind of does almost the same thing, but instead of looking at the determinant, it looks at the trace. So we have something called A-optimality. And A-optimality wants to minimize the trace of the matrix x transpose x inverse, with, I guess, little d's here to keep with my notation. Okay, so do you remember what the trace of a matrix is? The trace of a matrix is the sum of the diagonal. We'll put that in the side just to make sure we all remember that. The trace of M is the sum of the M, we'll say capital M, I. It's the sum of the elements on the diagonal. Now, x transpose x will necessarily have positive entries on the diagonal, so this has to be non-negative. It should be positive. If it was 0, it'd be very, that would be bad. But yeah, we don't want that to happen. But this is very similar, the reasoning. So if we ask ourselves, well, why would we want to do that? I'll say similar reasoning to de-optimality. Because if we go right back to this idea that the variance of our least squares estimator is in terms of x transpose x inverse, A optimality says, well, you know what we should do? Let's minimize the trace of that matrix. So yeah, that also seems pretty reasonable. How does it differ from the determinant? Well, they're not equivalent, but they're kind of doing the same type of thing. The determinant is by maximizing that determinant or minimizing the trace, we're both trying to, in some sense, shrink the variance of the least squares estimator as much as possible. That means we're going to get tighter confidence intervals. That means we're going to get more powerful statistical testing when we want to test for, well, significance of certain main or interaction effects. So again, those two things, very nice. You can also do something called T-optimality. Nope, I'm in blue. Let's do that in black. So we also have T-optimality. And this says that we can max the trace of that matrix, but not inverted, x transpose x. So then the point is this is same idea as A optimality, but not equivalent, I'll just say. You almost might think that you're going to get the exact same answer out. If you min and max the determinant of x transpose x or x transpose x inverse, you get the same answer because of the way determinants work. But the trace doesn't work that way. When you apply the inverse, the trace of the inverse is not the inverse of the trace, right? You can't just flip them like you can with, determinants. So the problem here is that you will get a slightly different answer for T optimality versus A optimality. Which one's better? I have no idea. I don't know if anyone strictly has a good reason. Maybe there's an interesting survey paper out there where somebody took the time to properly compare these methods. I'm not aware of one off the top of my head, but it would be something that would be interesting to try. Maybe if we have some extra time to kill at the end of this course, we'll actually test some of these on simulated data just to see what happens, because, they look almost equivalent, but again, the point is they are not strictly equivalent. And I think we have time for one more, just to give you a sense of all the crazy optimality criterion that are out there. Got the L, optimality. We have G optimality, and G optimality says I want to min the max. Min max shows up a lot in, I want to minimize the maximal element, the ith entry of the matrix X transpose X inverse X transpose, we're going to say I. So, okay. This is the ith diagonal entry of the matrix X transpose X inverse, X transpose. Now, what is that matrix? Well, if you've taken linear regression, sometimes this matrix is called the hat matrix, and you use it to, in some sense, translate between, you apply it to, in some sense, get a hat on things. But it also shows up as the variance of a prediction. So in linear regression, we would find out that the variance of y hat is going to equal something like sigma squared. Yeah, I guess I need to, we'll just write it out like this. It's not exactly 100% precise, but you get the rough idea. So the idea is, minimize the max prediction variance. So G optimality is doing something a little different. The first ones, the DAT optimalities, focus on, in some sense, they're focusing on the least squares estimator and saying we want to minimize the variance of our estimate as much as possible. G-optimality is doing, again, something very similar, but in this case, it's saying I want to minimize the worst possible prediction error rather than the estimation error or variance. So again, G-optimality, prediction variance. The other ones are estimation variance, but ultimately they're all kind of doing a very similar thing. Okay, so again, I don't have a good reason to choose one over the other, but it is good to know that there are lots out there. And if we go to Wikipedia, we'll find even more crazy optimality criterion, but a lot of them are typically based on the design matrix, because that's exactly what we're doing here. We're adding rows, right? When I say design matrix, I hope that was clear, but in case it wasn't clear, this is the design matrix. It has 2 to the k minus q plus t. This is the 2 to the k minus q, and this is my plus t rows, and it has k columns up here. So the question is, I have a matrix, I have some missing entries. What do I fill them in with? Well, here's 4 different choices for how to fill them in. Again, actually doing this by hand would be super annoying. Luckily, there are packages in R that allow you to do this. And again, the answer is not necessarily unique. You could have different settings for those rows that give you an equivalent optimality under one of these criterion. All right, so one more thing to talk about before we're done, and that's, but if we are interested in a specific factor, kind of like in my first example where I said, let's say we want to de-alias factor 1 or main effect 1 from its aliased interaction effects. So if we're interested in a specific factor, we could choose the T new rows to target that factor. Again, it's like if I find that 1 looks like it might be significant, then maybe I should target that specific factor with my follow-up data points. So then the question is, how do we do that? And we're going to do that now. But first, I did want to say one other thing that I realized I forgot to do up here. We also get a runs column. So we have a runs column. But one of the things we're going to note, and actually for all of the columns that I forgot to mention earlier, is that the columns are no longer balanced. So because we couldn't do an entire follow-up fold-over design, we no longer have balanced columns. That means that there's going to be some correlations when we go back and try to analyze our data in an ANOVA table. And that means we have to consider things like type 2 and type 3 ANOVA. Whereas before this, we could just ignore type 1, type 2, type 3 ANOVA because everything was balanced. When things aren't balanced, we have to consider that. All right, so in the final part of today's lecture, what we're going to do is look at choosing specific columns to target for our follow-up testing with respect to a certain optimality criterion. All right. In this case, I think, we're going to look at something called DS optimality. So in this case, it's going to be wrong color. We're going to look at DS optimality, which is just D optimality for 2 or more, but we're going to consider for 2 specific columns of the design matrix XD. So again, like I said when we were leading up to this, that if I have two columns or two main effects, let's say, that are of particular interest, and I want to make sure that they're not interfering with each other in some sense, I can target my follow-up tests, my follow-up data collection to focus on those two columns. So the setup is to write XD, our design matrix, in block form, where X1 is going to be a matrix which is going to have 2 to the k minus q plus t rows, and it's going to have k minus 2 columns, and X2 is going to also have 2 to the k minus q plus t rows and just 2 columns. So these 2 columns are the ones that we want to target our efforts towards. So what do we do? Well, first what we can do is we can consider block matrix multiplication, which is always a good time. And if we do a block matrix multiplication, again, what we're basically doing is we're taking the matrix, the X1 transpose X2 transpose, and multiplying it by X1 X2, and what we get out is a block matrix form, which is X1 transpose X1, X1 transpose X2, X2 transpose X1, and X2 transpose X2. Okay, so that's just the same matrix, X sub D transpose X, X transpose X, but written as in block matrix form. Now, the reason why we do that is because we can do a block matrix inverse, which I never remember the formula for, but luckily I have it written down, and you can always find it on Wikipedia or in textbooks. So if I want to invert this blockwise, well, I'm going to have 3 entries that I don't care about, which I'm just going to denote as star. The point is, I'm interested in the bottom right-hand entry because the bottom right-hand entry is going to correspond to X2 transpose X2. And that's those, I should say, are that matrix corresponds to the 2 columns that I'm interested in targeting my follow-up design on. So if we do block matrix inverse, we're going to get some kind of nasty looking equation, which is going to be X2 transpose X2 minus X2 transpose X1. And what else we have? X1, that's right, this is that hat matrix again. X1 transpose X1 inverse, X1 transpose X2, and the entire thing is inverted. Okay, so that looks kind of terrible. But what it means is that we can basically prioritize our follow-up design to target 2 specific columns by instead of maxing. Do I want to max? No, I should say, instead of maxing the determinant of X transpose X with the D's, we max the determinant of that matrix there without that inverse, which is just a whole bunch of X's here. Fighting our way through it. All right, cool. So basically that's what we can do. What we're doing here is we're saying, okay, I could just optimize for all the columns, or I could choose my 2 favorite columns and optimize for that. Again, it also doesn't have to be 2. in my example here, I just chose 2. We could choose 3, we could choose 4, we could choose k minus 1 and just leave one guy sad entry out for some reason. It really just depends on what we want to do. But the idea here is that we would just change the matrix the matrix determinant that we are trying to optimize with respect to. Otherwise, there's not much more going on with de-optimality. All right, so that is more or less everything I wanted to talk about with respect to follow-up designs and optimal designs for fractional factorial. The next thing we're going to be doing is doing 3 to the k factorial designs. They get a little bit crazier, so I hope these lectures kind of made sense, because it's about to get a lot worse next week when we jump into that 3 to the k designs. But so definitely ask me questions, contact me, ask me questions if you have any sticking points about this, if you want to do some more examples of aliasing, because I know that when you first see it, it can be a little confusing. And there's no way for me here to know if this all makes perfect sense, or if you're all just staring blankly into your screen like, what in the world is that guy talking about, right? Otherwise, yeah, I think that's more or less, I made all the points that I wanted to make. I kind of got cut off with the camera here when I was talking about this before. I did want to point out that, again, balanced design means that we have the same number of pluses and minuses in every column. Now, that is destroyed in the case of one of these follow-ups where we don't completely replicate the experiment. In the case that I completely replicated the experiment up here, we actually have balanced columns if we think of this as one giant 16-row design matrix. In this case, they are balanced. Even the runs column is balanced, which is nice. So we don't have to worry about any issues with respect to that. And actually, what I'm going to do is I'm going to just mention that down here at the bottom before we end, because I think this is an important point. Is that when, does the idea of balancing even make sense, right? I want to make sure that this is clear. When a design, let's say 2 to the k minus q design is balanced, we have that x transpose x is diagonal. That's pretty cool. And in fact, it's not just diagonal. Yeah, more so. X transpose x is actually equal to, well, what? It's going to be the sum of the column, I guess the number of columns. So it's going to be k. It is k, right? X transpose, let me make sure I got this right. No, it's going to be a k by k matrix where I'm going to be summing up. It's going to be 2 to the k minus q times the identity matrix. I here is the identity matrix, which is going to be k by k, not the identity element in my defining contrast subgroup. So hopefully that's not confusing. The point is that if I take one of these matrices up here, not that one's not balanced. If I take one of these matrices and I multiply it by itself, then what I'm going to be basically be doing is multiplying each column by doing a dot product of each column by itself. That's just going to sum up to be the number of rows. If I do a dot product between any two of these columns, distinct columns, I'm going to get 0 because I'm going to have the exact same number of minus minuses, minus pluses, plus minuses, and plus pluses being multiplied together. So effectively, if I were to do a dot product between these two, I'm going to get something like +4 minus 4 equals 0. If I did it with the entire 16-row matrix, I would have +8 minus 8 equal to 0 again. So this idea of balancing is really nice. It means that our design matrix, well, X transpose X is diagonal, our design matrix is orthogonal, has orthogonal columns. Therefore, the ordinary least squares estimator is, remember, what's the ordinary least squares estimator? It's going to be x transpose x inverse x transpose y. Well, in this case, x transpose x inverse is just going to be 1 over 2 to the k minus q, and then we're going to multiply x transpose y. So again, it makes things really nice. And when we consider the variance, which I wrote up above, the variance of beta hat is now going to just be an identity matrix. It's going to be, well, some constant, which is going to look like sigma squared over 2 to the k minus q, times the identity, which in this case, oh, it's going to be like 2 to the k, whatever. Yeah, it's going to be a big matrix. But the point is, it's diagonal, and that means there's no correlations between the individual estimators that I'm getting. All of my hypothesis tests uncorrelated. And if we continue to assume that all our errors are Gaussian, everything's independent, right? That's really cool. All of our tests, all of our estimates, all independent. And it's one of the reasons why when I start to play around with these designs, oftentimes the rows in the ANOVA table don't actually change. And that's a pretty neat thing. The problem is that when we jump into one of these cases, like my optimal choice of design here, we no longer have balance. So what we're going to end up with is, what we're going to end up with is going to be a non-diagonal matrix when we do x transpose x, or I guess more smartly said, we're going to have a design matrix whose columns are not orthogonal. And that means there will be correlations and more things that we have to take into account. So there's my rant on balanced designs and why I was so interested in having things balanced before when we talk about balanced block and balanced incomplete block and designs like that. But so yeah, ideally we can keep our design balanced. It's not always possible, so it is something good to keep in mind. What hazards arise when you have an unbalanced design? Now still, an unbalanced design when you're doing a follow-up experiment might be worthwhile because you're collecting more data, and you can use that to then get more evidence towards about your hypotheses. But there are still some issues to be aware of. It's good to be aware of those issues. And now we're going to stop, and we're going to pick up again in the next lecture where we get to talk about the 3 to the k factorial design. It's going to be a good time, so I'll see you there.